Good morning, everyone. I'd like to start with thanking the ScalaUA organization for pulling off this conference still with all the trouble in this that we're facing now. And yeah, really excited to do this talk. Stay healthy, everyone, right? We see a lot of a huge impact in Belgium as in many other countries, and it's really can't be safe enough. You know, this is it's really serious. All right, let's get started. So you see my screen, hopefully.
Yes, we can see.
All right, let's get going. So today I want to talk about two things, kind of related in a certain way, and those are Akka Typed and Dotty. I've been working with both, and pretty interesting. So let's start with Akka Typed. A big release was the Akka 2.6 release, which introduced, well, not introduced, but changed the status of Akka Typed, so typed actors API, from experimental to stable. And that's a major thing because the Akka Typed is really a dramatic improvement compared to Akka Classic. Then Java serialization was disabled by default. So as soon as you start communicating across a remote connection between actors, you have to basically implement serialization. And Akka provides a very neat way to do that with a Jackson-based serialization library with a CBOR binary format. Also with, it's just not a typed interface, all the main features of Akka, like Akka clustering, Akka cluster singleton sharding, cluster events routing, have new versions in typed versions of the APIs, and they're a big improvement. They are much simpler to use and much more robust. So we're going to look at a small experiment that I did with porting an Akka Classic application to Akka Typed. Dotty, as you know, Dotty is in full swing, in full development. When Dotty 0.21 release candidate 1 was released, it was declared feature complete. So unless something special happens, you know, really special happens, no features will be added or removed. Right now, we're at 0.23 with 0.24 in development. Projected release candidate, at which time Dotty will be kind of, you know, become an official Scala release. The 3.0 release is somewhere around the end of 2020, and we'll see how that pans out. But you know, time goes fast, so it's not that long away. During the presentation, I have to choose, you know, do I talk about Dotty, which is the thing that is happening right now? Scala 3 doesn't exist yet, but I may refer to Scala 3 to avoid flipping back and forth. If we talk about Dotty, we can look at it from two sides. We can look at it from an end user point of view, let's say, or a typical real application developer, or from the viewpoint of a library developer. But during this talk, we'll focus more on the application developer aspects. So when I started looking at Akka Typed, I had looked at the documentation, I looked at some simple examples, but you know, the trivial stuff doesn't bring you a lot of extra information. You have to really use it on a real project, and therefore I chose this project, the Akka Cluster project, which is a project that I use for training and meetups, in which we demonstrate in a visual way how clustering works. And I have, I can quickly stop the sharing. And so we're talking about a physical cluster like this, on which we have 5 Raspberry Pi nodes, and we have 5 10 LED strips on which we use to visualize stuff in the cluster. So that's the project I'm talking about. So I rewrote them to everything to Akka Typed using the functional style. There is also an object-oriented style, but I chose specifically to use the functional style. You could say it's non-trivial code. It's about, I think, about 1,200 lines of code, so it's not huge, but it's also not trivial. I did a straight port first, and then looked for room for improvement. So we'll see what I learned from the exercise. And if you want to know more about this project, there's a link in the presentation. I've updated this morning, so it may not, if you have downloaded a copy, it may not be there. So download a new copy. And it's a talk that I gave at Devox a year ago, last year, which is about this application. So the first experience was the complete, we now have complete protocol definitions. And what I mean by that is I'll quickly switch to an example. For example, here is an actor that has its protocol defined. So it's a ping pong actor, and we can send it a ping, and we also clearly define what this actor can send in response to other actors when it receives a message. And even though you could achieve this more or less by applying some convention, it was not really reinforced in Akka Classic, which is not very good. So these are, complete protocol definitions are a big win because it allows anyone who looks at your code to quickly understand what all the actors are doing and what messages they expect and what messages they can send back. Of course, if you have static typing, you can put that to your advantage when you're refactoring code. And that's something that I really experienced when I started enhancing the code. Moving to Akka Typed, an application from Classic to Akka Typed may also reveal some inconsistencies in your code. So in Akka Classic, anything goes basically, or almost anything goes. You can send, if you have access to a message of a certain actor, you can send it to any other actor. There's no reinforcement of the protocol. And actually, I discovered when I refactored my application that it was something not very logical. We'll get back to this immediately, but in Akka Typed, because of some limitations in Scala 2, we have to use so-called message adapters, which add some boilerplate. And it certainly in the beginning, when you start using them, it makes understanding code a little bit more difficult because there's a level of indirection that is added. But once you understand it, it's not a huge deal. Yeah, I talked about this, that there's many new features that, re-implementations of, for example, Akka cluster sharding in a typed version. Now, a fun anecdote to tell you about is that when I did the refactoring, I was, going through the code and changing it and compiling it, got compilers, and at a certain point, I managed to get my first error-free compilation. So then, the question is, if I launch the application now, will it actually do what it did in the past? And that turned out to be the case. So that it's something that Martin Odersky once said, that if your application compiles, there's a good chance that it actually runs correctly too. So let's dive into a little bit more detail. So as I said, in Classic, you need extra self-discipline because almost anything goes, right? But in Akka Type, we have to specify an actor's protocol. So here we see 2 actors, and the first actor, we can send it a command. It may respond. that actor may also send another command to another actor, which can send a response in turn. To make it a bit more concrete, let's take the classical hello world, the ping pong actor in Akka, where we have a pinger actor that can send a ping to a ping pong actor that can respond with a pong. And we have a non-actor, a main application that can send a send ping command, which will trigger the sending of a ping command to the ping pong actor. And then at some point in time, we may decide, okay, enough ping pong, and then we can send, then we can send a stop ping pong message, after which the whole system stops. Put it differently, these are the protocols of the two actors involved. We have a pinger actor that understands, that has a protocol. It has no response, but it has two commands, send ping and stop pinging. And there's the ping pong actor that understands ping commands and that can respond with a pong message. In Akka Typed, because of Akka Typed, you see that there is a problem that now pops up, because if we send a pong back in response to a ping message to the pinger actor, you see that the pong is not part of the protocol of the pinger actor. So how do we make the pinger actor understand the pong message? And that's something we can do using message adapters and message wrappers. So what we do is we extend the protocol of the pinger actor with a wrapped pong response that contains the actual pong. I say response here, but this is an ADT. So it understands the pong message, and then we hide this by making this message private to the outside world. So this is the code. It's pretty concise, quite different from Akka Classic, where the behavior is created immediately. Here, what we do is we define a behavior. For example, let's first look at the ping pong actor. We create a behavior here, and we create a new ping pong, and this actor can understand the ping message, but the ping message will bring with it the actor ref to which the response needs to be sent. So this is the reply to field. And so when the ping message is received, we send a pong message back to the sender of the message. And we continue supporting the same behavior. On the other side, on the pinger, it's a bit more involved in the sense that when we have a send ping message, we send a ping message to the other side. But we need to include our, an actor ref to which the ping pong actor can respond. So what we see here, as I said, there is a wrapper. So we have a final case class wrap response that contains the pong message actually, or that is part of the protocol, and actually this should be private. And so then in our behavior, what we do is we set up a wrapper which returns the proper actor ref. So it's an actor ref that can hold the pong message. And we have a message adapter method on our context text that we provide a function of the response that wraps it into the wrap response. And then finally, when we receive response, it will be wrapped in the wrapper, and we can take the response out. Yeah, actually, this was a zoom in. So it's the same slide, except that in this one, I have added the private because we don't want to extend our protocol by including the wrapper. So we can see that the message adapter solves the issue of being able to receive responses, but there is some extra boilerplate. And if you give your code to someone else to read it or to understand it, it will require an extra effort on part of the code reader to understand it. Is there a better solution? Well, we should be able to extend an actor's command set with the expected response type. That's not possible at present with Scala 2 and Akka, but there is some really promising thing that I will discuss shortly, thanks to Scala 3. When I moved the application, I had this, remember that I showed you this cluster, physical cluster with the LED strips. So if this is on a system, there is an LED strip that is driven by these green actors, and Akka Cluster provides messages. It's a subscription system that can give you messages that show you all the state changes. And this was implemented as one single actor, but as you can see, I've changed it since to a generic cluster status tracker that to which a visualizer actor that will actually drive the LED strip in the end can subscribe. Then it gets changes, and then there's an actual LED strip driver that does the physical commands on to control the LEDs. And we can also, pulse LEDs for a short time, and that is split up. So it has become very modular, and Akka Typed helped me a lot in refactoring this in a clean way. Another thing that I wanted to quickly talk to you about is on this cluster, I run a Sudoku solver, which is clustered. And we have, this is a Sudoku field. I'm not going to explain Sudoku, but if you implement a concurrent Sudoku solver, a typical problem you will be faced with is that you need to define a data structure, which will be a two-dimensional, for example, a vector of vectors. And then each element in the nested vector would, in my case, would be a set of all the values that are still possible in a particular cell. So that means that if you have algorithms that try to resolve, the state of rows and columns and blocks, you're faced with dealing with concurrent access to individual cells from different parts of your program. So I had this idea to, why not create actors, 27 of them in total, where 9 actors each look at a row, 9 actors each one of them looks at a specific column, and then 9 others each look at a specific block. And the way this works is that if we, for example, suppose that the 3rd or the 4th row actor gets an update in the 3rd cell, then it will, like you would do with pencil and paper, it will calculate the result, the consequences of that, and suppose that 2 other cells change as a consequence. What will happen is that this change will get communicated, and I'll show that in the next, in a few more slides, to the other actors. And now, the 6th column actor and the 8th column actors will repeat the same algorithm, and the 4th and the 5th, number 4 and 5th of the block actors will do the same thing. And so this propagates, each and every one of them applies the same algorithm, and you run through this. So the way it's physically implemented is that we have the 27 what I call Sudoku detail processors at the bottom. So we have 9 of them for the columns, 9 of them for the blocks, and 9 of them for the rows. Then we have the actual solver, which is basically nothing more than a coordinator. So a Sudoku problem sender sends an initial row update. So that's the known cells. And then the Sudoku solver will take those and send them as an update to the row processors. And in principle, but I'm not doing that in my version of the application, I could send these initial updates also to the other 18 detail processors. But I send it only to the row processors. They start applying the algorithm that I showed you in the previous step. And then either a particular detail processor can say, well, in response to what you send me as an update, nothing has changed. So that's a Sudoku detail unchanged message. Or it sends a row update containing new changes, and each row update will trigger an update to the other ones. So this was an algorithm, was like an idea, like, will this ever work? I implemented it and it turned out to give a solution. Then there's this one actor that I haven't discussed, this is a progress tracker. It's actually keeping track of all the updates in flight, and it will be able to detect when you reached an end state in which nothing changes anymore, and after which the result is collected from the row processors, sent back, and then back to the original problem sender. So actually on my cluster, I set it up so that each node runs one of these solvers that you saw. It uses buffering using a stash buffer and a group router to distribute loads between the different nodes. What I did learn is that I discovered an inconsistency. So I talked about the Sudoku detail unchanged message, but you see it appearing here, and that's odd. And I started looking at that, and let's see if I can quickly show that. Yeah, so here I have my Sudoku detail processor, and you see that the Sudoku detail unchanged is actually part of this of the detail processors, and not of the progress tracker. So that's an inconsistency. So what I did is I removed that and I replaced it with another message that is part of the protocol, which is this new updates in flight message. All right, accidentally clicked the next slide, but this brings us to Scala 3 and Dotty. So let's talk a bit about that. So first of all, what was the motivation for Scala 3? It's actually a complete redesign, almost from scratch, except for, I think, I would say the collection library, which it uses unmodified. There were some warts and inconsistencies in Scala 2, and also there was a definite need to reduce complexity and improve the user experience so that the learning curve can be lowered. A very important part of the Scala 2 or Scala 3 story is compatibility. If we look at binary compatibility specifically, it is possible with some limitations, but I've actually successfully applied this to use Scala 2 artifacts with Scala 3. And in the future, it will also be possible to do that in the other direction, so that this basically enables that you can gradually migrate to Scala 3 without having to wait until the whole ecosystem has provided Scala 3 versions of the libraries. There are and there will be more source rewrite tools to assist in migration. And then there is also a plan. So when 3.0 comes out, some Scala 2 features will be deprecated and they will effectively be removed in the next release. So for example, in 3.1. Tooling, where it's early days, but there is, for example, Scasti that already supports Dotty. If you want to start playing, there's a SBT Sample Project, and all the blue underlined things in my slides are actual links, so you can click through to get to those subjects. Visual Code Studio is already supported as the IDE supporting Dotty. And there's no metal support yet, but that should be coming soon. IntelliJ did not really support Dotty, but, and it's what I actually just ran when I switched to IntelliJ. I ran release 2020.1 RC1, which has support for Dotty. A few features, top-level definitions. So this is because package objects are deprecated in Dotty, and they are replaced by top-level definitions, which means that you can have, for example, methods defined at the package level. Main functions. So instead of having the extends app or an object that implements a main method with the right signature. So there's main functions. I will briefly talk about that. Extension methods that are part of contextual abstractions have been completely overhauled, and there are definitely a big improvement. Optional braces syntax support. Let's look at that in a second. And then very important, union and intersection types. If you want to look at the complete list of things that are new in Dotty, you can go to the Dotty reference. So top-level definitions and main functions. Package objects will still be around initially. They're deprecated. So we can have, apart from classes, objects, and traits, we can have implicit values, type classes, definitions, and values. Oops. And then by annotating any method with the @main annotation, turns it into a message, a method that can be an executable program. And it can take an arbitrary number of arguments that are also type checked. A little bit about extension methods, a new syntax. So the old syntax is still supported with the implicit class syntax, but extension methods are defined as follows. Let's zoom in. So we see, for example, specifically we have two case classes, a member that takes an ID as a string and a case class cluster. This is the way that we define an extension method. So the exact syntax is still subject to discussion. For example, they actually recommend putting a dot in between here now. So if we want to define an extension method called merge on an instance of type cluster, we do it by inserting something which looks like an argument list in between the def and the method. So this definition defines an extension method called merge that takes an argument on an element of type cluster. And then we have the implementation in which we generate a new cluster that is the join of the members of the two clusters. And then we have another extension method called addMember, which allows you to add a specific member. So with this, we can do something like, create a cluster and calling the addMember with a member and merge it with a second cluster. Because we don't have enough time, I'm not actually going to show that in the REPL. Optional braces support. So it's actually indentation-based syntax. So you can obviously compare it to Python, and the compiler enables you to rewrite code from the braces based in a syntax to indentation-based syntax and back. I'm not going to talk about the new control syntax, but there's a new way to do an if then else, for example, where you explicitly use the then keyword. This is my favorite feature, as you will soon understand, and it's called union type. So it's a new kind of type. And here's the definition that I basically copied from the documentation. So union type A, union B, or I tend to read it as A or B, has all values of type A and also all values of type B. So here's a small example. Let me actually show you in the REPL, because I want to show you some action. So if I go to the REPL, and here I'm in a project that is using Dotty 0.23 to be precise. Voila, if I paste this code in here, I have now defined two ADTs, a tools ADT that contains a hammer and a screwdriver, and tool supplies, which is a nail and a screw. So if I now go back, and I have this print method, I paste it in here. You see that the print method takes an argument named T, which is the union of type is a union of the tools type and the tool supply type. And I can pattern match if I have a case it's a tool of type tools or a tool supply. I either say got a tool or got a supply, and let's try that out. So if I say print it and I pass it hammer, it will say got a tool. If I say and I pass it a 9-inch nail, I get a supply, which is a nail 9. Okay, so that's pretty cool. But what can we use it for in the context of our presentation? Actually, we now can go back to Akka, and remember we had this message wrappers and protocol adapters. So we can actually achieve this, something which is much simpler by saying, okay, this actor not only understands its commands, but it also understands the response from the ping pong actor. And then there is a small remark that we need to make, but we'll get back to that a little bit in a few moments. So how would you implement that? And this is basically how it looks like. So nothing has changed on the right side in the ping pong actor, but on the left side, and let's zoom in, we have our protocol. And now I define an extended protocol, which is commands and responses, which is a union of the command and the response. So now we define a behavior that is of the type that I just defined, and now we can transparently understand the response. So is this all that there is to it? Well, not really. We can say, have we reached our goal? But there is one issue. We've polluted the pinger actors protocol. So how can we fix that? So this is how it looks right now when we use the Akka 2.6 library. And so what we do is we say, okay, this was already there. We have, and that's the change now, our behavior is of type commands, but we create a behavior that is the union of command and the response. And then we see this funny guy at the end, which is a dot narrow. And this is something that is because of Scala 2, because there is actually no reason, if we would implement this in an ideal way, that we would need this narrow method. And let's quickly jump to the code. Not this one, but this one. So let's go to the pinger actor. So we're in the pinger actor here, and we see that we have set up our behavior of type command. We actually do the setup with the extended protocol, and then we do the narrow. Now, if we look in detail at behaviors, that's the source code. We see that the type here, oh no, sorry, that's on the wrong page. I need to do behavior. Voila, behavior. It's generic, so it takes a type parameter t, but you see it's declared as invariant, which it should actually, and there's a remark here somewhere that says that it's actually ideally it should be declared as contravariant, because if it would be declared as contravariant, and because of we wouldn't have the Scala limitations, Scala 2 limitation that prevents us from doing that, we would be able to write exactly the same code, but without having to do this dot narrow. And that would be a tremendous change, because it wouldn't get any simpler than what we have on this slide. Conclusions. Akka Typed is a huge improvement on Akka Classic. So it helps us to reinforce service domain. Remember that I made this mistake, and I detected it actually by migrating to Akka Typed. Obviously, it's a huge help in refactoring or changing your application. And the major Akka APIs have been re-implemented, which has led to a huge simplification, much cleaner APIs, and much less prone to errors. Message adapters add some overhead, but the promise is that Scala 3 will eliminate this completely. Scala 3, as we saw, it removes some words and inconsistencies. It brings simplified syntax. It has a great compatibility story. Well, it still has to be fully delivered, but it looks extremely promising. And the tooling situation is improving and should get really exciting. And that's it. And much to my surprise, I'm concluding early. But I can throw in a quick demonstration of this application, I have a standalone version here of the Sudoku solver, and it's actually clustered. And remember that, you know, I'm going to run it in this window, so I can start up an instance. This is instance 0. The exercise was exercise 12. So if I run it here, it will start up, and it will start solving Sudoku. So there's the problem generator is continuously sending messages, and you also see this dropping requests passing by, and that's because I'm sending Sudokus at a higher rate than a single Sudoku solver can handle. So the stash buffer, which you may recall, actually fills up quite fast and then overflows, which is signaled by the dropping of a request. But if I start up another one, so I take instance 1, I start up yet another one, and yet another one, we will see that after JIT does its work, things will become to a point where requests are no longer dropped. And you should see, well, the thing is I'm using a lot of CPU also for the Zoom session, so it may never, yeah, it's actually getting there. You see, it's no longer dropping stuff. And we see the result being printed here. It's also, you know, pretty robust. If I, you know, the Sudoku solver, a problem generator is running in this on this node, and if I stop it, I'll hit Control-C, it will be automatically detected, and another, it's still stopping, I think, yeah, it stopped, and you should see that the problem sender has now sender has now moved to this node. All right. Really weird that I'm finishing early, but that concludes my presentation. If we go to the presentation, we go to the very beginning, you see that on the 4th slide, there is this link to Akka cluster. So if we open that link, it's this project. And it's actually the project that has the, you know, all the code for the Raspberry Pi cluster based on, based on Raspberry Pi with the LED strips and so on. So if you want to run that code, you will need to build that cluster, and you need the LED strips. But I would say stay tuned, because we may be able to supply you should you be interested in getting them. I have another repository. But it's currently private, in which I did, you know, an extraction of just the Sudoku solver. It was actually the code that I just ran in the 4 terminals, and I will probably open it up as is soon, so that you can run this, you know, just on your local laptop. What else? Yeah, let's look at the messages. Stop sharing. On your personal opinion, are Scala 3 plus typed Akka ready to use? Okay, so Akka typed is definitely, it's fully supported. Scala 3 in production, I wouldn't do that, because it's not there yet, and you would be running a Dotty release. But there is actually something now that you ask me, something pretty interesting. There's this, let me go back to sharing my screen. Voila, to quickly finish. There's this pull request that was recently submitted on the Akka project, Dotty syntax compatibility, and it's a huge PR. You know, lots of files have changed, but it's actually making Akka compile on Dotty. Pretty amazing. So, you know, keep an eye on this. I'll actually quickly paste it in the Slack channel. Voila, should you wish to have a look at it. And with that, I think we can call it a day, for at least for this presentation. All right. Thank you.
Thank you. Thank you, Eric.
Thank you.
Presentation.
Thank you. It was a cool presentation.
Thank you.
Thank you.
Thank you very much.
All right. Let's
Great
go to
short.
the next one.
Great short.
Bye.